All right, so in this video, we're going to be looking at how to do projections onto a subspace. We have other examples where we project it onto a single vector, which I guess technically is also a subspace. But we're going to be looking at projecting onto a subspace which is more than one-dimensional. And the basic idea here is you're going to project onto the individual vectors of the subspace and then remove any part of the vector which is already in the span, and then that will give you those components that are in the span, and then the remainder will be those components that are not in the span. Now, for this process, we should start with a orthogonal basis for the subspace. So I've checked in a previous video example that these are, in fact, if you dot them together, the two vectors in H are orthogonal. 1, -1, 2, -2, they all add up to 0. So these are already orthogonal to each other. That's going to make our life much easier. And so now what we're going to do essentially is we're going to project onto H, we're going to project onto V1, and then we're going to project onto V2, and then those components will give us projections that are in the subspace. We add those together, and that will give us everything that we can get out of U that is in H, and then we'll calculate the orthogonal complement from that in order to get that part of U which is not in H. So projecting onto the subspace. So first what we're going to do, as I said, is we're going to find the projection onto V1 of U, and we're going to find the projection of onto V2 of U. So let's do those formulas. If you recall, the formulas are U dot V1 divided by the magnitude of V1 squared times the vector V1, and likewise the formula for projecting onto V2 is exactly the same, except we change all of our subscripts. So let's see what happens here when we actually do this. So if I dot V1 with U, I'm going to get 2, -1 and 3 is -3, 2 and 4 is 8, and -2 and 1 is -2, divided by, I'm going to look at my V1 and I'm going to square all the components, and I'm not going to take the square root. So it's going to be 1 + 1 + 4 + 4. And then I'm going to multiply all of that. So let's put parentheses around it because this is going to be a constant. This is essentially our scaling factor, and multiply by V1. So what are we going to end up with? We're going to end up with 2 - 2 is 0, 8 - 2 is 6, and we're going to divide by 10, which is 3/5, which is going to give me 3/5, -3/5, 6/5, and -6/5. Now, because these are divided by 5, you can represent these accurately in decimal form, but there's no guarantee that that is normal or standard or happens on a regular basis. You can get other weird fractions. So for right now, I'm just going to leave them as fractions. And if I repeat this calculation for u times v2, let's go see if we can find, so that's 1, 1, 1. So that'll be 2 plus 3 plus 4 plus 1 divided by 1 plus 1 plus 1 plus 1 times our v2 vector. If we simplify that, we get 10 over 4, which is going to be 5 over 2, which is going to give us 5 over 2, 5 over 2, 5 over 2, and 5 over 2. Now, in order to get the projection onto the entire subspace, then we're going to add up the projection onto one vector plus the projection onto the other vector. And so we're going to add this vector to this vector. And so let's see what we get. 3 divided by 5 minus 5 divided by 2 is going to be negative 19 over 10. And negative 3 divided by 5 plus 5 divided by 2. Oh, wait, sorry. 3 divided by 5 plus 5 divided by 2 is 3.1, which is 31 over 10. Sorry about that. Let's try this again. Negative 3 divided by 5 plus 5 divided by 2 is going to be positive 19 over 10. And then 6 divided by 5 plus 5 divided by 2 is going to be 3.7 or 37 over 10. And negative 6 divided by 5 plus 5 divided by 2 is going to be 1.3 or 13 divided by 10. So this will be our projection onto the subspace. I sometimes notate this to help me keep track of the notation as U with a subscript that is a parallel marker. And the reason that I do that is because this reminds me that this is a vector which is in the subspace. And the perpendicular component, the orthogonal complement, is the original vector minus the projection. And that is a vector which is orthogonal to the space. And so to indicate that, I will indicate that using a perpendicular notation, because that is the vector which is perpendicular to the subspace. And so that is going to be our original vector, this guy. U minus U parallel. So again, this is the projection into the subspace. This is the original vector. And then if we subtract these, then we can get the part that is not in the subspace and therefore is orthogonal to it. So 2 minus 31 divided by 10 is going to be negative 1.1 or negative 11 over 10. And 3 minus 19 divided by 10 is going to be, again, 1.1, 11 divided by 10. And 4 minus 37 divided by 10 is going to give me 3 divided by 10. And 1 minus 13 divided by 10 is going to give me negative 3 divided by 10. And so what we would expect then is that this vector would be not only orthogonal to the projection, but that it would also be orthogonal to either of the two original vectors in our example. And if we're thinking of this as a part of a basis, we can go ahead and rescale it. But if we're just looking for the projection of this particular vector onto the space, we can't clear the fractions. We can't multiply by 10 because if we cleared all the fractions, then the two vectors wouldn't add up to the original vector anymore. So as a projection and an orthogonal complement, we have to leave it be. But as I said, if we're trying to find a basis, maybe we want to find a vector that is in, let's say, W perp. The orthogonal complement to the projection onto the subspace would be a component of the perpendicular subspace vector W perp. And then we would be able to use this as our third vector and then find a fourth vector to fill out the rest of W perp. So there are lots of ways to find these vector spaces and bases for those vector spaces. But for the orthogonal complement for the given vector, we would stop here.